What do we know of A and B? If two people are sitting on a merry-go-round at the same time, which one of them is moving faster in terms of their angular velocity? None of them. Okay, how about this? What does it take for me to go around the Earth once? If I'm here, it's angular. How about if I'm in Bogota, Colombia? How about if I'm Juneau, Alaska? Well, for me to get one rotation of the Earth is the same amount of time. You see what I mean? So it's like the rotations of the Earth is all the same time because we're all in the same thing, rotating at the same time, at the same rate. So what is true about the angular velocity of A and B? They're equal. Does that make sense to you? Okay. Now, can you see this in your mind? That this thing is going to spin like this. Now, when this little wheel takes one rotation, does the big wheel take one rotation? No. Does that make sense? Right? That the big wheel's angular velocity is going to be less than the little wheel's angular velocity. Because what is causing this whole system to turn? That weight. So when this weight turns this little disc once, this big wheel has only turned like maybe half or something. I don't know. Let me see. Pi times the diameter. So this, the circumference of this one, the circumference of the big one is, I don't know, 0.2 pi. And the circumference of the little wheel is 0.1 pi. Yeah, okay. So this is twice the circumference. So this little wheel has to turn twice before the big wheel turns once. Does that make sense? So while this is turning, the angular velocity of the little wheel is bigger than the angular velocity of the big wheel. Now that allows us to do a couple of things. Okay? Because we know that angular velocity, right, is related. And how are they related? What do you do to angular velocity to get linear velocity? How about this? What do you do to linear velocity to get angular velocity? What did we do to linear measurements to get rotational stuff? Divide by the radius. Because what is the measurement of the change in angular displacement? What is the angle measurement for math? You use it every day. Radians, right? Remember for the first, most of the fin here with your calculator set in radians, and you go to degrees, you're like, oh, what's going on? Do you remember this? I think this happened to most people at one point or another. Because then we start doing trig, and then all of our trig is in degrees. Okay, I guess not. Hopefully we remember that omega is equal to V over R. So that means V, what the fudge? It's lagtastic. So omega, or V is omega times R. Is everybody cool with that? Sorry? Omega is like V. If you go back to your notes from that thing, you'll notice I didn't do an equal sign. I drew like an arrow. And then the one that we did do the equal sign was this. Omega is V over R. So here, omega, right? Omega B is less than omega C. Now, if we multiply both of these by the radius, how much bigger is omega B than omega C? I said it. Yeah, twice, right? Oh, I'm sorry. I said that wrong. How many times bigger is omega C than omega B? Because remember I said this has to go around twice for this to go around once? So that means this must be twice as fast angularly as this. How much bigger is the radius of this than this? twice. What happens when you multiply a number that is half as big times twice the size of radius? Yeah, they're going to equal each other. These two are, in fact, equal. And think about this for just a second. If you're an ant on the big wheel, and there's another ant on the little wheel, right? In one amount, like 1 second, like each other, 1 second later, like running at the same velocity, aren't you just going to stay right next to each other? See, it's because the two wheels are touching each other. Because of friction, there is a one-to-one displacement, right? So in terms of meters per second, the same number of meters have to pass per second on both wheels, even though the omegas are different. So a little bit interesting, but if you think about it, slipping, if this travels like whatever, 1 meter, this should travel 1 meter. It just means that this one turns more than that one. But their linear velocities are the same. Questions? Have I lost anybody on that one? I mean, you can think of it like if you're pulling and pushing a merry-go-round, and the merry-go-round on the outside, a kid sort of, I don't know, GPS, right? And the GPS thing is telling them how fast they're going. And they're going at 5 meters per second. And you're the one pushing the merry-go-round. How fast must you be going? 5 meters per second, because you're connected to the merry-go-round, right? Does that make sense? You can't go a different speed than that kid on the outside of the merry-go-round. Same thing here. If this wheel is moving at 1 meter per second and it's touching the other wheel and they're not slipping, does it make sense to you that they must be going the same speed? That's the logic behind that problem. And what we did was we said, hey, look, we used the omegas to figure that out. Because omega b is half omega c. But radius b is twice radius c. And when we multiply them both together, the halves and the twos cancel, and we get the same. So we did it with math. Now, inside here, okay, let's do this. I mentioned, let's say here in San Gabriel, all right, am I traveling the full circumference of the Earth at like the equator circumference of the Earth in 24 hours? So yeah, no, right? Do you see that in 24 hours, a person at the Earth's equator, is that in Bogota, Colombia? Somewhere in Colombia, I'm sure, is closer to the equator than here. Do you see that in 24 hours, because like the Earth's rotating like this, right? They're here and we're here. And this is what Alex mentioned, right? He said, wait a minute, we're not traveling as far in 24 hours as this person. And then somebody in Juneau, Alaska is traveling even less far in 24. We all go how many rotations? 1. But do you see that we all have different miles of travel? Our distance traveled is different. So the smaller your radius, the slower your velocity. And this is why, right, like if you're on a merry-go-round, if you want the maximum like vomiting effect, where do you go? Yeah, like you get on the very outside, you put your feet on the outside, hold on with your hands and do this. Right, actually, if you want the maximum vomiting effect, like do that, but then put your hands in. That's a good one. Yeah, exactly. So here, which one is moving faster? And imagine that you're looking at the Earth from the top view. This is like Bogota, Colombia. And this is like Anchorage. Hey, look at that. Bogota, Anchorage. And this is like Alaska. In 24 hours, who travels in the smaller circle? Anchorage. Do you see that? So this is true. The velocity on the periphery is greater than the linear velocity of something on the interior, especially if they're on the same thing. This stuff takes a little bit of time to kind of get your head to understand it. I mean, if you just look at this, you're like, oh yeah, that makes sense. Cool. You're smarter than I am. But that's not a big deal. Don't get too excited. All right, next comes this for linear acceleration between B and C. Yeah.
Is that why the back is the best on roller coasters? You move faster. Instead of being in the middle, you don't experience as much.
Interesting. I've wondered this. I think it's because of like a transfer of energy, like a whip. Yeah. So like when you go down the hill, like the front is pulling, so that you're getting just a slight bit more. I don't know.
Yeah, the front's the worst.
Yeah. Yeah, it depends on your perspective. It's funny, like, gosh, how many times, oh crap, I forgot, knots. Yeah, I gotta start, oh shoot, I gotta start quick. Could you run the board, knots, knots physics fun day? Yeah, there's a field trip that we always go on called Knott's Physics Fun Day. It's gonna cost like maybe between 30 and 35 bucks, it depends, okay? But I mean, that includes, it's the bus to get down there, and we leave school at 7 a.m. and we get there at 8. From 8 to 10, the only people in Knott's are physics students. So what you can usually do is just walk right up to rides and go. Okay, if we get there at 8, we get there at the crack of 8, it's like just run up to a ride, boom, Ghost Rider, bam, get in and go. Some rides, they let you just get off, get back in. But, you know, so that, and then we come home around, like we leave Knott's around 3:30 and get home around 5. So if you are in, you will miss a day of track. And it's gonna be either March 3rd or March 10th, I'll let you know. So yeah, that should be a fun day. It's always fun. I used to ride the roller coasters. I no longer ride the roller coasters because I'm bored of them, so now I just go eat chicken.
You had Pinks.
Huh?
Pinks.
I had Pinks. It's okay. It wasn't
Yeah.
like a religious experience or anything. Oh, great. I'm recording all that. Awesome. Okay, well, that's good, because then the other class will hear about Knott's Physics Fun Day and hot dogs. For E, this one, the acceleration of B and C, if the velocities are the same, does it make sense to you that the accelerations have to be the same? Right? It's like, again, if you are accelerating that kid so that one with the GPS is on the outside of the merry-go-round, and he's saying, okay, you're going this speed, you're going this speed, and it's increasing, you must be doing that increasing as well. But for A and B, I think we can also say that if your angular velocity is increasing, then the acceleration of this one, is this going to be more or less than this? Well, how do you get, what's the way to, oh, we know that, does it make sense to everyone that alpha B has to equal alpha A? Does that make sense? The angular acceleration of both of those things must be the same. If he wants to go for the vomit effect, so he grabs onto the outside, and then Layla's like, vomit, not so much, on the inside. And they're at rest. And when I grab the thing and move it, is it possible for him to angularly accelerate faster than her? Angularly. No, because they're both going to turn at the same rate, regardless of how fast I push or pull it, right? Linearly, yes, they're different, right? Because his circle is smaller than hers, but angularly, they're the same. So if we say this is true, well, then we say, what is A of B? Well, isn't that alpha B times R of B? And then A of A is alpha A times RA. Right? And since alpha A and these are the same, basically it's a function of the radius. Like